Wow, where is everybody?
Asleep, I don't know.
Sad. OK. And today we'll reveal, the secrets to all of foundation models. No, just kidding. OK, we're going to do eval today. Just some logistics. So homework 2, I hear folks talking about it. It's due next week. For presentations, actually, a lot of people signed up. We're at like 73% of the class signed up. If you hadn't had a chance to yet, please do that. I'll release project information this week as well, hopefully tonight. We'll have a sign-up sheet of a similar type. You guys will have something where you propose your ideal project to me. Other than that, not too much else. We have a few more lectures left. So eval today. We'll talk about agents and some more reasoning next week. And then we'll kind of move into other topics. So multimodal, scaling laws, et cetera. Anybody have questions about where we're at? All right, let's do it. OK, so a bunch of things for eval. I'll start talking about what makes LLM and foundation model evals more complex than traditional machine learning eval. As a result, this is a pretty big topic, and it's a huge research area on its own. So we'll talk about kind of what you need for a good benchmark. We'll talk about some popular benchmarks that are used for all new models that come out. So human eval, MLU, Helm, these are all kind of well-known benchmarks that you'll use. And then we'll kind of move on into how do we do things a bit more automatically, which means that we're not stuck with a static kind of benchmark. Instead, we can do something more dynamically, where we can essentially create the benchmark in real time. And the way we'll do that is using LLMs essentially to provide for us some grading, some way of determining whether the model being evaluated is doing good or bad. So that will be this idea of LLM as a judge. And then we'll see that there are some issues with this method, and we'll try to think of things for fixing them. And then I'll talk a little bit about variations. There's a bunch of well-known popular benchmarks that are sort of combinations of different eval mechanisms. And then we'll talk about agentic benchmarks, which are kind of their own beast. All right, so let's jump in with the first part. All right, so if we go back to standard ML, 760 supervised learning type of stuff, eval is something very, very simple, right? So what do you really do? You take all of your data, you train on some of it, but you have a holdout set that you test on. And that's really all that eval amounts to, right? I have my trained model. I have some points that it hasn't seen during training. I go ahead and run my trained model on those points and compute some average performance. And that can be accuracy, it can be F1 score, it can be a whole bunch of different metrics. But the training points and the evaluation points are really the same kind of points. In fact, ideally, they're IID from the same distribution, right? So all of this is relatively simple for traditional ML, right? You can do other things like cross-validation. You can switch to other metrics. All of this stuff is fairly basic. You can even do non-scalar metrics, like you can write a confusion matrix like we saw. Now, you can do these with foundation models as well, but only in more limited scenarios, right? So one of the things we're going to deal with for language models is answers that are not really just a single prediction, where you can easily say that was accurate or not accurate. In fact, the space of possible generations is very large. So that's the thing that we're going to have to deal with that makes things a lot more complex than what you're seeing here. More importantly, the training mechanism for all our models is very different from the evaluation mechanism, right? If we do pre-training, we don't really care too much about how good the trained model is on that pretext task that we pre-trained on. So things have to be different when we do evaluation for foundation models and for large language models. Everybody agree with this? All right, cool. So let's see some examples. Things are going to be more complex for us. We have very general capabilities, right, for our foundation models. That's the whole reason for them in the first place. And having these general capabilities means we have a lot more work to do to try to test them. Then the space of typical generations for a generative model is really big, right? It's not as simple as saying there's K classes. I'm predicting one of those K classes. Let's test how good we are at that. In fact, the biggest issue we're going to have is that lots of different answers could all still be correct. If I tell my model, solve this mathematical problem and give me a proof, right? There's lots of ways of writing that proof that are all correct. So I can't just say, here's one golden solution. Go check that you predicted every token in it correctly. There's lots of possible solutions that are all equally good. I have to account for all of these. And it's unlikely I can write them all down and say, did you hit one of those guys? All right, so let's try to categorize what might be useful for an evaluation system. And it really is going to be a system in this case. Of course, we're still going to need some data, but it doesn't have to be necessarily holdout data from training. It can be something more complicated. I'm going to need some metric that we go measure. But again, the metric could be something more complex than just accuracy. And in fact, very often what we'll do is have a whole bunch of different metrics and look at all of them. And then the last piece, and the most important, is we'll need some mechanism that actually goes and computes these metrics on our model. And this mechanism can end up being something fairly complex, and very often it's quite expensive. The simplest thing you can do, of course, is just show the outputs to an expert who's a human and have them say, are they good or are they bad, or give some more fine-grained determination. But that's super expensive and it doesn't scale. So usually we'll have to design some mechanism that's both accurate in some sense, but also is scalable. So it can't be very expensive. All right, everybody agree that these are the goals that we're going to have? All right, so what's an example of a type of evaluator that we already built in this class, but in a different context? Yes, right? When we did RLHF, we tried to figure out if the generations coming out of a model are something that humans prefer or not, right? And to do that, we did train a reward model, which can act as an evaluation system, as a mechanism. And in fact, very often we will use reward models to figure out if our generations are good. But usually reward models are not meant to check for correctness or accuracy. They're usually meant to check for other things that are more holistic. Right? So things like, are these generations typically polite, friendly, helpful, et cetera? So we'll see more things that we can do here. All right, so let's jump in and see these three different components of an eval system in some of the classic cases that everybody used for eval for LLMs for quite a while. So the first one I'll show is called human eval. This is 5 years old. You don't typically use it anymore, although sometimes you do. It's basically something that was done for code. From the very beginning of building large language models, the idea that they could output code was pretty exciting. Now, initially, these large language models were not yet very good at outputting code out of the box. So if you just pre-train GPT-3, it doesn't really have great code abilities. And some of the earliest work was just about kind of building on top of a base LLM to give it code abilities. Now, today's LLMs are kind of trained on huge amounts of code anyway, so they always have lots of code capability anyhow. But that was not the case about 5 years ago. And Codex was a model that fine-tuned GPT-3 to try to make sure it's actually good at outputting code. Now, to test its abilities, this human eval data set was introduced. And as you'll see, it's something that's kind of tiny, but it's already getting at this hard problem of how do you evaluate open-ended output like code, right? So there's lots of ways to write good code. There's lots of different programs or functions that all pass test cases. So I do need something here that can't be just, here's a golden solution, compare against it. OK, so let's see an example of the kind of problems that were built into this human eval data set. They're all fairly simple because these code abilities were initially kind of simplistic. So here's a problem where you're given a list, and you're supposed to basically add or increment each element by 1, right? I mean, this is trivial, of course. Every language model today can do this very easily. But this was not super easy for the earlier language models from 5 years ago. All right, everybody OK with this kind of example? So we're covering the data. And soon we'll need to talk about all the other mechanisms that we use for measurements, right? So for the total data set, it's just 160 handwritten problems. And you might ask, well, why didn't they synthetically generate a whole bunch of different problems? And the answer is also that that was pretty hard back then. So someone actually had to sit down and craft all of these problems by hand. So 160 is a reasonable size at that time. Today's data sets tend to be much, much bigger, but you're still kind of limited by how much time you can get from human experts. Each of these problems has a definition that's given to the model that's being evaluated. It has some metadata, and then it has some test cases. And our goal is going to be, let's pass those test cases. So this is not too different from what we saw in RLVR. It's just here we're doing it for evaluation purposes only, not because we'll go train the model on these things. All right, everybody OK with this? Pretty simple data set. OK, so what kind of things do we see in it? Programming tasks. They're going to basically figure out if the model can understand what's being asked for and do some very basic math. Nothing too complicated, right? Here's an example of what you want to see. Okay. The next part that we need are metrics, and here's where things get a little bit more interesting. The most sort of standard metric you might ask for here is just accuracy, right? If I give my model this problem, does it get it right or wrong? And I average that over the entire data set. By itself, that's actually not super interesting. There's very, very high variance, right, in how often you get it right. And what's more interesting really is saying, hey, let's go ahead and run the model multiple times on the same problem, generate several solutions, and see if one of those is correct. That's really getting more at the core of the model's capability, right? Now, suppose my model is not super good, but still 10% of the time it'll provide the right solution for a problem. That's actually still very interesting to know about. But if I only ever ask it once, things are not nearly as interesting. It'll often just get it wrong. So pass set k says k samples, does anything pass from those k? If so, then you pass that problem. And what you'll typically do for this is, rather than just doing it once on just a single draw of k solutions, you'll really do it multiple times and average over subsets. Right? So for example, you could generate n samples, and then what you're going to do here is say, okay, well, in any subset of 100 of those, is there a passing solution? Any questions about this? All right, so the reason we're doing this is just for variance reasons, right? If we just go ahead and say, hey, let's draw one single subset of k, there might be a solution, there might not be, but the variance is very high there. So if we draw many subsets of k and average over them, then our variance is much lower. Now, okay, are we really going to take every combination of 100 solutions from a set of 200? Probably not, right? We'll just take a few draws and take the sample average. But really what we're trying to estimate here is just this guy. We're basically saying, hey, if there's c solutions out of n that pass, then what is the chance that we actually end up not getting any of them right? And let's do 1 minus that. So that's what you're seeing in this combinatorial expression. What I'm going to do is say, okay, well, I'm taking k choices out of the full n solutions that I've generated. What's the chance that none of them are right? Well, to draw a subset that has no correct solutions, there's n minus c incorrect solutions. I have to take k of those guys. So the fraction is n minus c choose k over n choose k. This is the chance of getting stuff that's all wrong. The chance I get any of them being correct is 1 minus that guy. So this is the thing that we're trying to compute. But of course, we're not going to directly actually compute this because we're not going to go look at every single k element subset out of the n total solutions we generate. We're just going to sample a few times and approximate this pass set k. OK, a little bit of probability. Anybody confused by this? Go for it.
Do we actually take subsamples, or do we just use the percentages that pass to calculate the expected value for the pass k?
Well, how would you calculate the expected value?
Oh, right.
So of course, if you actually go do this and look at all c, you can actually do it, right? But normally, you're not going to do it if n is sufficiently large here. OK, so this is pass set k, nothing special, but very common in coding and other hard problems. I'll show an example of some curves. The other thing that we're missing in our three elements that we talked about, which were data, metrics, and mechanism, is we need to actually go run these programs, right? And to do that, we're usually going to use some kind of sandbox environment. And it's literally just go run the programs and see what happens here, right? Let me show you some curves. This is something that we're going to see a lot more of when we talk about scaling laws. But what you're seeing here basically is for different amounts of parameters in our model, different model sizes, how well do we do when it comes to pass set 1? So this says I'm only getting one program, one solution, and I want to see if it's right or wrong. So this is the hardest kind of test for my model, right? If I do pass at 100, then I'm just saying, hey, you have to get it right 1 out of 100 times. Here, I'm actually asking it to get it right all the time. So let's see what happens. If we have small models, 10 to the 5, 10 to the 6, et cetera, we do very poorly. That's not surprising, right? These are also older models. Those model sizes are way too small. But if we keep making the model larger and larger, we're starting to do better. Now, notice that the base GPT-3 model, which doesn't have coding capabilities, is really stuck at 0 the whole time. Even at full size, 10 billion parameters over here, there is no gain in performance because it just doesn't have those capabilities. You can do whatever you want with it. It can't answer coding questions because it doesn't know about code. Every other curve you're seeing that's not the blue curve is one of the codex models in different settings. So this is the fine-tuned version of GPT-3 that does actually have coding capabilities. So not surprisingly, you are getting performance lift as your model gets bigger. OK, now there's some interesting pieces here. Right? So one of the things that's happening is essentially that we're saying, hey, what if I do generate more programs, not just a single sample, but then I have to choose one to go evaluate? So this is actually different from pass add k, because in pass add k, it doesn't matter which one you've created, right? As long as any of them triggers and is correct, you're fine. Here, we're telling the model, hey, you must pick one of your generations, and that is the one that we're going to evaluate and score you on, right? So think of a test where you have 5 different solutions you come up with to a problem. Now, if I'm going to be very friendly, I'll look at all 5 solutions. If any of them is correct, I'll say, great, you pass. However, that's very generous, right? Normally, what you have to do is pick out the solution you want to submit. And if it's wrong, then it doesn't matter that you had a different one that was correct. Everybody see what I mean by that? So this says, OK, well, the model can generate more solutions, but it has to pick on its own the one that is going to be scored. And so how do you do that? Well, there's a couple of different ways, right? You always want to rank your solutions using whatever information you have internally. And when you go rank your solutions, you can say something like, hey, maybe based on the confidence scores, you can literally look at the probabilities, right? I can say, hey, which one of these is the most likely? And I'll pick that one. So that's this log p re-ranking that you're seeing, the red curve. And notice that this is actually quite a bit better over the green and orange curve, which are just generate one solution. Now, one question we might be wondering is, OK, well, let's suppose that someone actually told me the best solution that I have, right? In that case, what would happen? That's that purple curve of an oracle that you see on top. Now, we don't know how to do this, right? Because we don't have an oracle that externally says this is your best solution. But if we did, we could do a lot better as well. And we get up to 80% performance, which is pretty good. OK, so this is a story for human eval. As I said, this is not a data set we're currently really anchoring on, but you'll still see it included in a number of papers. The only downsides are, 1, it's getting pretty easy. So most models can just do everything. And for that reason, you're saturated, right? The benchmark's not that useful anymore. And 2, the other piece that's kind of annoying here is these are all problems that are now older, and models have seen them before, right? So now they've been kind of trained on stuff that looks very similar. You're no longer getting as good of a gauge anymore. OK, so let's see another example that's not code related. This is a very, very popular data set, MMLU. So this is also coming from about 5 years ago. And it's really much more of a question answering language capability type of benchmark. It's not specialized to code at all. It's more about just measuring how much the model knows about different categories. And there's a few different ways you can run this, right? Just kind of going back to when we talked about prompting, you can do 0 shot or few shot with this one. And you kind of do it across a lot of different areas. Let me show you what those areas look like. Everything you're seeing on the left over here is telling you different categories that this big data set contains questions from. So US foreign policy, history, sociology, business, college math, et cetera. Think of one of these like GRE subject tests or what have you, right? With lots and lots and lots of different categories. And we're really asking, hey, how good is my model at knowing stuff from all of these different areas? So it's fairly big, which is nice. It's 16,000 total questions. It wasn't created, right, de novo. Nobody sat and actually wrote new problems. This was just kind of scraped and pulled together from different sources. So there were pre-existing things like admissions tests for college or other college tests, et cetera. They pulled all those questions together and kind of put them into a common format. OK, so there, as you can see, if you're going back to 5 years ago, this is, again, GPT-3, which was what was being tested back then. You get between 25%, and this is multiple choice, so that's random chance, all the way up to being able to get to, apparently, foreign policies especially easy, 65%, whatever. So there's pretty good variation across domains here. It gives you a sense of what models are good at, what models are not good at, et cetera. Now, again, same problem as human eval. This benchmark has been largely saturated. Models have gotten pretty good at it. It's not extremely useful anymore to just directly test on MMLU. But if you're building, for example, a very small model, then MMLU is still kind of useful, right? Because it can be pretty challenging for a much smaller model. It is not challenging for GPT-5. There's no point in trying it out there. OK, so let's see some other examples. The way that you actually do scoring here is that you have multiple choice with 4 options. And you do have a validation and test split. No training data, because again, this is evaluation. We're not trying to train on anything. But for making choices about how we deploy our model, we do have a small set of validation questions. Everything else is kept for the test split. That's really what you'll be running this on. So multiple choice is going to be very simple here. It's exactly what you think. Here's a college math problem, right? It's about complex numbers. In the complex z-plane, the set of points that satisfy this equation looks like what, right? And it's giving you some choices. So the model needs to do a couple of things. It has to read the actual problem itself. It has to be able to understand it to some extent. And then it has to be able to parse these different options and pick the best one. And if you can do this, then you'll pass. And if you cannot, then you'll fail. And it's pretty useful for determining kind of where the model will struggle. All right, everybody agree with this? And notice this multiple choice thing is very useful, right? Makes it much easier to be able to go out and actually score the model, because I can just check, did the model get it right or did it get it wrong? There are not too many choices, and scoring becomes trivial. Cool, so let's see some other kind of challenges which are very interesting about it. Since we're doing multiple choice, we want to do accuracy, right? And we can compute accuracy over all the questions within one of these 50-some domains, and then we can kind of put them together, right? And the sort of early results look like this. So if you do few shot, which means you do get to show some multiple choice examples to the model in the prompt before you actually ask the question, then models that are up to 13 billion parameters basically were random, which means they have no actual information. They're just guessing randomly. But bigger models already, even back then, could get up to a non-trivial accuracy. So if you're doing multiple choice and your answer options are balanced, 25% is just random guessing. If you are substantially above random guessing, that means the model actually knows something. OK, everybody OK with this part? Go for it.
What are the modern models benchmarks on MMLU today? Like, what's GPT-5 getting?
Probably over 90%. I don't know if that's like, there's sort of follow-ups to MMLU. I'll show an example, which is what people really play with. I don't even know if they report MMLU performance. I'm sure someone's tested it. It's really easy to run. But you should be able to get over 90% easily. There's a caveat, which is there's lots of errors in the data set. So there are questions where the answer that's given is wrong. And if you answer it correctly, which GPT-5 will actually do, you're marked down. So you actually cannot get to 100% here unless you've really memorized the answers, which sometimes happens. Yep.
How do you know that 25% is random, what it is now?
Well, there's 4 multiple choice options, right? And it's consistent in the sense that each option shows up about equally likely. So you end up getting, if you just guess randomly every single time, 1 in 4 tries you'll get it right. Or if you just answer A every single time. Yep.
If there is a parsing error from the model, like we expect it to give it in some way.
Coming up on the next slide. Yes. That's one of the major annoyances, actually, of all of these things, is forcing the model to give you an answer that's formatted in the way that you want. All right, so this so far, at least, is accuracy. So this is really very similar to classical ML. And that's why for a long time, multiple choice was really preferred for question answering type stuff. OK, so let's see some of the details of how you actually create the mechanism. So the first thing you're going to have to do is to craft prompts that you give to the model. This is the information that comes in addition to the actual question itself, right? So typically, it's not just like you're showing the question and the answers. You also have to give some instructions to the model, just like we talked about in prompting. Same idea here, right? And the text is going to be the following are multiple choice questions with answers about the particular subject that this question is coming from. OK? Then you end your prompt with answer, colon. This is to encourage the model to just go ahead and output that answer. And then here's the more interesting part, right? The model really has the ability to put any text whatsoever, any token after the answer, right? So how should we try to figure this out? Well, basically, we're going to look for the probabilities of tokens to try to parse a final answer from this. So whatever is in there, we're going to say, hey, well, even if you didn't actually answer A, B, C, D correctly, what has more probability for that last token position? And if the correct answer shows up, then maybe you can give it a pass. Otherwise, no. And this is something that's actually kind of annoying. We'll see there's more examples to kind of help out with formatting and parsing. You also have two settings, right? So you can do zero shot, where you just have the multiple choice question, or you can do few shot, where you include some sample questions in the prompt to help the model figure out what it's supposed to do. So this is kind of it here. There's nothing special about it besides this kind of 5 demonstration examples. Let's see some of the annoying issues real quick. So let me show you an example of a follow-up that is actually being used today and also is going to improve some of the bugs that we just talked about. This one's called MMLU Pro. It's from last year. One issue is, again, the fact that these old benchmarks are too easy, and models have figured out everything about them. So let's make things a little bit harder. And ideally, let's make things also more consistent, in the sense that if we ask the same question multiple times, that we get the same answer more often. In other words, let's try to reduce the variance of the answers from the model for each question. So this is what MMLU Pro tries to do. Here's some comparisons between traditional MMLU and the new version. So one is over here just looking at saturation. The orange curve on the left, that's MMLU. This is with free models. None of these are reasoning models, right? So we're not asking the model to go do a bunch of problem solving. We're just telling it, give the right answer. So as you can see, basically you have 70%, 80% or more for all of these models for MMLU. And that really could mean 100%, given how often some of the problems are wrong. For the blue version, which is the new benchmark, you have much lower performance, which is good. You're also seeing the trend that you kind of expect here. A closed source model, which is quite powerful, 4.0 is the best. And then Llama Free, the mid-range model, 70B, is also pretty good, but not as good. And then a much smaller model that you can deploy at home on a single GPU, like Gemma 7B, it is quite a bit lower. So this is kind of the expected performance that you typically will see. All of these are still decent performance, even on MMLU Pro itself. Of course, let me explain what random guessing means here. You might say, hey, it's below 25%. Isn't that really bad? In this case, they replaced the 4 options with 10 options. So random guessing is now 10%. Right? So random guessing is not as effective anymore. And if you see something that's above 20%, 30%, it means it's actually pretty meaningful performance. OK, so the other bit I wanted to show basically is over here. These distributions that you're seeing, these involve basically just taking the model, asking the same question repeatedly, and seeing kind of what happens and how often you get different results. As you can see for MMLU, the traditional one, the distribution is much more spread out, but it's much lower variance for MMLU Pro itself. I saw a question. Go for it. Oh, that's what the model actually tells you, right? The model is just going to generate a bunch of probabilities for every conceivable token in your vocabulary, and you have access to that. Of course, you're going to sample one of those guys with whatever sampling mechanism to actually produce that token, but you don't have to, right? Cool. All right, so one more thing that these guys did is they said, hey, let's also consider questions that do require some form of reasoning, and therefore we can run all these models with chain of thought mode as well. Think back to when we talked about let's think step by step and so forth. Same basic idea here. And it's kind of nice to see whether or not you get a big benefit from chain of thought. For MMLU, the questions were all so simple that really there's no great importance to having chain of thought included. For MMLU Pro, you actually do see a difference, because for some domains, as we've seen before, there is a benefit from doing chain of thought. And of course, current models have thinking mode, reasoning mode built in, so they'll also be able to take advantage of this as well. All right, so MMLU Pro is a good bit better. Let's see some details of this. So instead of the 4 choices that we talked about for MMLU, we now have 10 choices. So random guessing is not nearly as effective. The other bit as well is that these answer choices are often designed in a way that they can kind of fool models, right? So often I'll create these what are called distractor options that for the model look good, but really are the wrong answer. And of course, this is what we do when we create tests for students as well. But models are especially attracted to certain key terms, so it's often very easy to fool them. And having 9 incorrect answer options means you have a lot more room to come up with different scenarios to fool the model with. So this is actually much more helpful for being challenging for models. Then there's the chain of thought thing that I mentioned. So MMLU was before chain of thought really existed as a technique. So therefore, there wasn't a big reason to include questions that require that. MMLU Pro actually has a bunch of these questions. And then finally, there's also the question of just quality, right? Do these questions make sense? Are they coherent? Do they have a single unique correct answer? Is that single unique correct answer in the list of answer options? These things sound very obvious, and they are, but actually they're a pretty big problem. This kind of noise issue shows up in data sets a lot, and a huge part of MMLU is just wrong answers, or questions that really don't have an answer, or questions that have an answer, but it's not any of the answer choices. So yeah, don't be too dependent on hill climbing on a single benchmark, because becoming too good at it might not indicate what you want. In fact, it might make your model worse potentially. OK, and the other piece here is the formatting thing that we talked about. So rather than looking at token probabilities, what these guys do basically is they kind of allow more flexibility. You just look for one of the answer options A through J. There's 10 of these options, so you need 10 letters. And you do a little bit of parsing to try to go figure out, is one of those letters somewhere in the answer token sequence? So a little bit more flexibility here. Currently, what people do is they'll parse the output with another LLM and depend on that to see if the answer's in there. Cool. All right, does this sound good for everybody? And this is actually used all the time. In fact, when we were talking about those hybrid models earlier, one of the plots that we showed was looking at performance on MMLU Pro. OK, so some results. These are from the paper, which is from last year, so it doesn't have all the new models. But you can get a sense of this stuff for different categories. So 4.0 is pretty good, 72% overall. Again, 10 answer choices, right? So random guessing isn't giving you a big boost here. You're getting pretty good at math and physics, kind of worse at law, which is very specific and kind of domain bound. But still not too bad. 55% engineering, which again suggests that it doesn't know as much about different areas of engineering. Similar results for Gemini, for Claude 3, which are these big closed source models. And then when you move down to open source models, the performance is actually not really that bad when you look at something like Llama 3. And I should mention that Llama 3, which was last fall, about a year ago, that was sort of the point where a powerful open source model was maybe the very closest that we had to sort of frontier closed source model performance. And then immediately after this, reasoning models came out, and then the gap expanded, and then R1 closed it further. But we're still probably a little bit further in terms of open source to closed source gap. OK, this makes sense for everybody? And this is the kind of like set of results that you typically generate from a single benchmark. As you can see, it's not just one number. We're going to try to break it out into a bunch of different categories and figure out what are the weak spots. And in fact, data sets like this are what the frontier companies really use. They'll look at this kind of result and say, I need some questions from engineering to get better at it. And they'll go out and commission a giant data set of engineering problems, and they'll train their model on that. So a big part of sort of the spending they do is just data creation. All right, let's see one more example of another MMLU follow-up work. It's called MMLU Redux. This one is much more focused on looking at the actual issues within the traditional MMLU. And really what they want to do here is to find bad questions and fix them, right? So rather than designing a whole new data set, let's just go ahead and see what issues there are and fix them all. OK, so there's a bunch of these examples that I was mentioning, right? There's cases where the actual answer that MMLU gives is just the wrong one. And the actual correct answer is there, but they didn't realize it, or there was some error in whatever they marked. The other options might be things like, hey, all the answers are incorrect. In other cases, the question might be ambiguous, right? It might not have really a single way of answering it. So there's lots of examples of this from MMLU itself. People sometimes actually commission sort of independent experts to go verify different data sets. And really, whenever someone goes out and does this, you can always find bugs in data sets. There's another popular recent one. It's called HLE, Humanity's Last Exam, which is a very pompous title. For that one, someone essentially sat down and looked at their chemistry problems and realized about 30% of them are wrong. So this is very, very standard, unfortunately. This is why benchmarking is extremely hard, and knowing that your model is good is just not easy. Every evaluation mechanism tends to be very noisy. All right, so let's keep going. Let's see some of what these guys did. By throwing out all of these bad problems and improving a subset of other ones, they end up with a much smaller data set, so 3,000 questions compared to over 10,000, but it's a lot better. And really, it's actually better to have a small data set that's trustworthy than having this giant data set that has all kinds of flaws and is giving you unreliable results for your model. Okay, so let me show you kind of what these guys do. I like this process, and this is really getting much more into the data curation part of foundation models. Essentially, they have this sort of top-down flow where they start for a problem, and they say, OK, let's first check if the question has decent presentation, is it posed correctly at all. And if not, then you either throw it out or you have to clarify it from the top. Let's check to make sure that all of the answer options make sense, right, and are coherent. And if not, you have to fix those guys. Let's check to make sure that there is at least one correct answer, but not more than one, right? Same thing here. You have to choose the answer options and correct them if that's not the case. Check to see that the actual answer you picked really indeed is correct, and so forth. So this is a process that they follow. And this process is really something that you do have to implement. You have to create sort of a flow that experts can go out so they can create high-quality questions. In fact, data vendors really have an internal process that looks exactly like this. All right, any questions about all these MMLUs out there? Go for it.
Are we doing this with LLM or
Say again?
are we doing this with an LLM, like the verification?
No, this is manual. Now, there are ways of doing that as well, and we'll talk about automating this process. But really, in the end, the problem is any LLM is itself unreliable. So if you want to have very high confidence that something's correct, you need a human expert reviewer. Otherwise, you can't be sure. Cool. There's, by the way, like 10 more MMLU variants of different types. So if you want to pick one, just make sure you have one that you actually have confidence in. OK, so we've talked a lot about individual benchmarks. But of course, any single benchmark by itself is not really enough to feel good about your model. So even if it's broad, you really want to go bigger than that. So as a result, you typically want to assemble a collection of these benchmarks and make some kind of evaluation judgment based on that. And this is what Helm is doing, so holistic evaluation of language models. This is one of the most popular ongoing projects that incorporates a ton of different benchmarks with different metrics and so forth. And the way you go out and use Helm is you say, hey, there's particular metrics or axes that I want to evaluate my model against. Let me go look up in this kind of table which data sets make sense for me to look at as a result. And you create this big sort of overall aggregation of suitable benchmarks, and you push them all together. So Helm in total has something like 200 different component benchmarks, and there's more that get added in all the time. It just gives you a way of doing something over a very broad range of different evaluations. Cool. OK, so I'll stop here, and then we'll start talking about LLM as a judge, but we can all take a 5-minute break. And I can answer more questions.
All right, I'm going to ask you to fill this up for me while you're out. But
Yeah, just a lot of manual work. Right. I mean, you look for each new benchmark that comes out. You look at, okay, here are the metrics that here are the domains that are being used. Here's the kind of models that can go ahead and evaluate with it. And then just say database.
Yeah, I guess like for the bias tracer, I'm more curious about the right end axes because there are things just like variance, bias, how is there
No, each data set has their own. But some of them are consistent across data sets.
Yeah.
But yeah, you have to figure out what is fairness, bias, etc. Right? I mean, a lot of them are, they're not standardized where there's like a rule they can do, but they all have the same sort of code. Right? For example, for bias, you're going to look at different populations, gender, things like that. Right? It's going to show up all over the place. All right, we'll see. So they're easily consistent with each other. This is just saying, hey, there's these different data sets out there, right? So whatever these are. And they're saying, hey, well, what kind of metrics are these data sets compatible? What can they tell me? And they're giving you this big table that tells you which ones are. We're going to test LLM against these things, but first we want to figure out, well, which data sets should I go use? And this was a statement. Like, supposedly I want to go and say, hey, I want accuracy. What data sets measure accuracy? Well, all these guys do is I asked the same question. Well, how often do I get different? Would I always get exactly the same answer? Let me look at this. Am I constantly getting different results? But I have very high variance. Now, the problem here is it's fine if it has high variance, but if I just draw a single sample, that's too risky. So to deal with high variance, I'll actually have to go and draw many, many samples, right? And that's expensive. I don't want to do that for my model. So I want data sets that has lower variance as a result. And that's what these guys are saying. Yeah, go search through them and see if they're right. Hopefully it doesn't. There's ways to check for that too. Do I see capital letters A through G? There's multiple conscious options. That means those are bigger. It's kind of like up to us in design, right? You can say, hey, first appearance of capital with where I accept that one as even if something that's or I can say, hey, they can only do one appearance. If there's more than one, it's like that's sort of entirely includes.
I just want to let you know I ended up running what caused a massive performance issue. It was e-float to float cast that was taking, casting literally the entire weekend proceeds backwards and forwards and CPU.
Very interesting. Why? That's a weird one.
Because gaming GPUs from the 2X series only do floating point operations on float 16, not the float 16.
I would never have thought of that. So I'm glad that you tested that. That's super interesting.
I found out because of warning it's bad Alex, to be fair.
Even better.
What GPU were you using?
Warning. RTX 2, your associated graphics unit doesn't support float operations. It has to.
Okay, I guess that exact same species is taking a long time too.
Yeah.
So I think that might be to do with your use it.
I have on the code platform.
All of our
Oh, so just ended up not.
Yeah, I was able to test I was able to train a 4 billion parameter model.
But if you do want to use that whole
Is it? That said, I do learn to float at the beginning.
Yeah, I did it to float 16, but then it took twice as long.
Interesting.
And I tried it on the CPU also, and it took twice as long.
Yeah. Well, yeah.
Like 1,000 times.
And
Yeah, but I mean, very much.
they're not.
I'll just only do 1,000.
I mean, if that becomes
I was gonna
But for these very large model providers like OpenAI, Anthropic, Google, they do those biggest models.
was not existed. Yeah.
so like how did you
Yeah, I just edited the code.
I was like,
There was a time where it was supposed to be
And they want to compute it
over
sizes for fancy GPU.
but I tried to does support deflow. It says true.
Yeah.
So
I checked that as well.
yeah.
Oh my
yeah.
God.
I mean, she's one to say.
To configure your it's so their code that I use sets a vocab size equal to the number of distinct characters rather than the number of characters.
All right, everybody ready? Let's go ahead and talk about automating evaluation. So this is the task of let's get rid of like either static benchmarks that were created by a human expert, or alternatively, let's get rid of having to ask an expert again and again to give us new evaluations. So we'll do it with something called LLM as a judge, but it's a fancy term for I'm going to ask another model to evaluate the first model. So it's a little bit of the blind leading the blind here, but we'll see that it can sometimes at least be reliable. Okay, so here's the basic idea. We want to build our own benchmark ideally for every task, right? That's not really going to be easy unless you have tons and tons of resources, and even then. So we'd have to acquire data, we'd have to select our metric, we'd have to develop the mechanism. It's going to be very painful, right? So the thing that we're going to ask is, if we had access to an oracle, we could do it certainly, but we don't. We have no human experts because they're too expensive. Well, let's just go ahead and use another model to go ahead and do this judging. And it's fast, certainly. It's relatively cheap compared to hiring a human expert, although ironically, it's actually not that cheap, right? Because if I do have to go and use another model to look at every generation, that itself is another API call, another large number of tokens I have to pass through a model. And if I want my judge model to be very reliable, I should use the most powerful model conceivable, right? And conveniently, that's also the most expensive model. So really, actually doing LLM as a judge is surprisingly expensive. And very often, you have to pay, I don't know, hundreds of dollars to evaluate on one particular benchmark, which is not by itself very expensive. But if you're doing this repeatedly, the costs add up. OK, so let's go take a look at this idea. People really started doing this quite a bit in about 2023. So here's an example. In this case, I'm not going to just evaluate a single model output and give it a score. I'm going to do a comparison, which is very similar to what we were doing back when we were talking about reward modeling and preferences, right? Except this time, instead of handing it off to a human expert, or just some human and say, do you prefer A or B, I'm going to ask another model. So here we have a question, right? It's basically saying, hey, there's 3 of these cases or whatever. The first assistant, which is another LLM, is saying, OK, here's the answer. The second assistant is giving me another answer. I have some follow-up questions, right? I can do multiple of these things. And now finally, I bring in a judge, which is GPT-4, and I tell them, hey, is A better than B, or B better than A? And also, what should we do to improve? So notice how flexible this is. Instead of having a fixed question with a fixed set of answers, and that's it, I can do much more complicated things, right? I can do a conversation that has multiple turns. It has follow-up questions. So this is something that I can do in much more general scenarios. But what's the cost that I pay for it? Well, I can't be completely confident about GPT-4's judgment. It is itself a model. It will make mistakes. So this is the trade-off that we're doing. We're going to be much more flexible, much faster, much more dynamic, but we can't be totally sure that we're actually getting a meaningful assessment out of the judge model. OK, everybody OK with this idea? Cool, and this is actually extremely popular. So I can either directly evaluate one model, or as I said, I can compare a pair of models. This comparison is one of the most popular ways of evaluating models. There's these cases of what are called LLM arenas, where we have models compete against each other, and we compute how often one beats the other. So this metric is called the win rate, and we very often try to establish what is the best model and has the highest win rate. So we'll see this all the time, but this is exactly how we do it. OK, so we don't need close-ended questions. We can make things completely open. Any answer is OK. As long as it can be consumed by the judge model, we're fine. We can have very long responses here. We're not worried about that at all. And there's lots of different ways of doing it, but this is like the main paper for it. Pairwise comparisons, which was what I mentioned. Single answer grading, so you just give a single answer response. And finally, when we have access to a solution, we can say, hey, how close are you to that solution? In fact, this is actually one of the most convenient things about LLM as a judge. Previously, if we had a full solution to a math problem, it was very difficult for us to evaluate, right? We could say, hey, did you predict that exact solution, yes or no? But that doesn't tell you anything, because a slight kind of rewording would still be good. In this case, we can actually do that comparison. We can say, hey, the LLM provided the solution. Does it capture everything that's necessary from this correct ground truth solution? So these are kind of the free ways of using LLM as a judge. It just depends on the case that you're going for. If you do have these ground truth solutions in specialized kinds of settings, you want to use the reference guided. If you actually have some meaningful scoring mechanism, you want to use a single answer. And finally, pairwise is just very popular for kind of establishing general capabilities for a model. And for LLM Arena, people actually did a whole lot of this. OK, everybody OK with what we can do with LLM as a judge? And again, before you go run it on everything, ask your advisor about expected costs and all that. Yeah. Let's talk about some of the issues, including that one. Go for it. it has to be superior in the sense of the area it's judging on, right? It doesn't have to be strictly better in every way, but it has to know more about whatever it's judging the model on. Otherwise, yes, you're going to be even less reliable. All right, so some of the issues, I mentioned cost, okay? One issue that's really funny is LLMs get confused by things. In fact, this is what we talked about in like lecture 4 or so, right? So we said things like the position of various things inside a prompt matters quite a lot. And here, the prompt consists of the generations from the model we're evaluating. So this really can be a big issue. It's also a big issue of MMLU itself, by the way, right? So models are more likely to answer A, which comes first in a multiple choice list. And therefore, if the correct answer is more often A, you'll get artificially high performance, for example. Right? So you have these issues. There are examples of biases that you get. These are not as bad in more modern models, but they still actually accidentally exist, right? So you're more likely to pick the first option as correct, whether or not it's actually correct. Okay, some other issues. There's this kind of bias towards very long responses, right? So LLMs like very comprehensive responses. So if I have two outputs that I'm comparing, one is actually incorrect, but it's very long and detailed. One is correct but short. The LLM judge will typically prefer this longer one. So it's very easy to trick it for that reason. And in fact, a very vague, long response is often the winner in LLM's judge. Okay, another example is that LLMs tend to like their own answers, which should make sense, right? I mean, if they're more likely to generate something, they'll also be more likely to say that it's good. As a result, basically, if you're having human outputs compete against LLM outputs, even if the human ones are really good, the LLM output will be favored quite often. And finally, there's kind of the biggest issue of all, which is maybe my judge just does not know about the area that it's supposed to grade in which case is going to make random guesses, and you really cannot rely on it at all. So these are all the issues. This doesn't mean that you can't use LLM as a judge. It does mean that you want to think about these things, be aware of them, and make sure that you're not falling into that trap. So how can you deal with these things? Well, you can do different things, for example, right? Like you can control how long the answers are from the models that you're evaluating. In that case, you won't run into this verbosity bias. You can make sure that the model you're using as a judge is not one of the models that you're evaluating. You don't have that self-enhancement issue. And finally, you probably want to test your judge on some other data set or some other set of questions to make sure its capabilities are good enough, right? Otherwise, you can't rely on it. All right, so let's see some examples. How do we know that LLM as a judge will actually work? We're going to get into this recursive issue, right? We have to evaluate the evaluator. And if the first evaluator is itself an LLM, we have to evaluate that and so forth, right? So this is going to get something very, very complex. But the real way that we're going to do it is let's, at some point, throw out a reliance just on models. And let's see if our judge is acting the way that human experts actually would. And as you can see, now we're back to our starting point. We said we don't want to deal with human experts because they're expensive and not scalable. Well, we're kind of stuck with it at some point, right? So the nice thing here is we can try to say, let's get a small set of human judgments. It doesn't have to be a full data set, which might be too expensive. Let's use the small set, and let's use it to compare so that our judge, at least on this smaller set, is behaving the same way that humans do, right? And this is just a basic correlation. And if it works out OK, then maybe we can feel confident that on everything else we're using the judge, it would act the way that humans do as well. So you're getting some examples of these correlations right now. The red over there is kind of the human, and you're seeing different models, so GPT-4 judge, GPT 3.5 judge, et cetera. This is also a multi-turn data set. So it's evaluating kind of the quality of the first turn, then the second turn, then overall, and so forth. Generally, these things are reasonably correlated. We especially want the blue curve and the red curve to kind of match up, which they mostly do, although it's not completely perfect. But this is typically what you'll have to do. If you introduce some new LLM as a judge-based system, get 100 questions and do query human experts and prove to yourself that the judge is behaving like humans. If they are, then you have some degree of confidence that it'll do that for the rest of that data set. Okay, so this is kind of the way you do this. Now, people do a lot more additional studies to figure out what the weak spots are for judges. Okay, so inconsistency and bias, of course, is not too surprising. A bunch of examples of cases where LLM as judge is not quite good enough to be human level. Positional biases, etc. You can see a bunch of nice examples here. People often work on sort of adversarial ways of fooling judges. I mentioned that length or verbosity thing, but there's other cases as well, right? So this is a case of like asking a very simplistic question, what is the square root of 36? Well, you can introduce a bunch of mistakes in there that the judge doesn't realize, right? So for example, in the first case over there, you're getting something wrong, but you're sort of saying it in a very confident way. In that case, the judge will be fooled by it. In the second case, you have something that is wrong and nonsensical, but the judge allows it to pass, etc. So lots of different sort of ways that you can fool a judge with if you're willing to do this kind of adversarial study. Okay, so a bunch more of these. You can replace a judge with a whole collection of judges. This is getting back to that idea of majority vote, right? Hopefully one of the judges is more often right, and you can use that. There's theoretical guarantees for this. You can personalize judges to behave as if they are a particular human. Very big area of research, even today. And you kind of have to really eventually move to LLM as a judge for most forms of evaluation. So there is going to be a lot more research on this until we're pretty confident at using it. Okay, let's take another 2-minute break. Any questions about LLM as a judge? Cool, in that case, let's do it. I have a few more slides on variations, including some new data sets and some new benchmarks. This is going to be basically stuff where we try to take some of the principles that we've had so far, static expert-created data sets plus LLM as a judge. So here's kind of an example that was very popular for a while. It's called Alpaca Eval. It has this leaderboard that was kind of the main leaderboard for people competing with. But basically what they did was they said, hey, let's see how often a powerful LLM prefers the outputs from that model over the outputs from some reference model. So they have some fixed reference model. I go ahead and say, hey, I'm going to provide my own model, and we'll see what that win rate looks like. How often am I better than their reference? And then someone else competing will have their own model. They'll compute their own win rate against the same reference. And if I'm better, then I'll say, hey, I win 60% of the time over the reference. They win 50% of the time, or what have you. OK, so let me show you some examples. I took the screenshot last year, but you'll see a pretty interesting example. So here's what you're seeing for win rate, all against GPT-4. Different variants will get up to 57%, et cetera. If you go down to some of these open source models, it can be much lower, so 38%. Now, there's 2 columns here, which is kind of interesting. It turned out basically that this leaderboard was also affected by that verbosity thing, where producing very long answers tended to give an artificially high win rate. So the column on the right was the win rate not really accounting for that. And at some point, people started introducing models that just explicitly made very long responses on purpose. And those were getting very high win rates. So they had to move to this column, which is length-controlled win rate. So this has some normalization that says that if you're too long, we're going to penalize you, actually. And this actually changes, and you can probably see the rankings are quite different for the left column versus the right column. So this is one of the most popular benchmarks, at least for quite a while. Now, this one, unfortunately, is another thing that's very annoying, because if you're going to call a judge model all the time to see what is preferred versus not preferred, you actually do have to pay a bunch of money, right? Because we're going to make tons and tons of calls to a very powerful model. So submitting to Alpaca Eval, I think it used to cost like $150 for like one submission. So you can't do too many of these things, and you can't try to totally overwhelm this kind of benchmark. OK, so you can also do this for models that are sort of user-created, and this is what people are having fun doing. I can take an open source model and play with it. I can fine-tune it some more. I can give it some new capabilities. And then I can go submit it on a benchmark like this and see how good I can do. Some people figured out an adversarial technique that always gives you wins. That's the thing on top over there, 86% win rate, right? Again, another instance of trying to hack the LLM as a judge system. But there's a bunch of other examples that are actually quite interesting. So take Gemma, for example, which is Google's open source model, add a bunch of techniques. MOA is mixture of agents, which is an interesting technique where I can sort of generate multiple responses, aggregate them, generate multiple responses like that, re-aggregate. It's this hierarchical technique. That turned out to work really, really well. It has very high win rates. So yeah, for quite a while, people really loved experimenting with this kind of leaderboard and trying to create new tricks to give a higher and higher performance. OK, cool. Much more stuff than this. I do want to spend a couple of minutes on agentic benchmarks. Now, for agentic benchmarks, things are going to be a little bit different because the whole point of an agent, and we'll talk more about this next week, is that it's not just answering questions and being evaluated on the quality of those answers. Instead, the agent has to go operate in some environment, right? So things are now different. I'm saying, hey, take an LLM, use it as an agent, put it into some scenario, some environment, and make it do stuff there. So now when I'm evaluating it, it's not a question of did it give the right answer. It's a question of did it do the right things in that environment. So this creates even more complexity for evaluation compared to everything we've seen so far. And as a result, it's a lot more work to create any of these things. So the most popular example, which really kicked off all of these agentic benchmarks, is called Web Arena. And what it does basically is give agents access to the internet, but not the real internet, more like a restricted fake version. So this is a web sandbox. And let me show you an example. Basically, you create a bunch of copies of websites from different domains. And these have applications. So the agent can actually interact with them as if it's a human user that was going to these websites. So you can have things like a fake Reddit. You can have things like a fake shopping website like an Amazon, et cetera. The agent is literally operating on the web. And it can take actions, like it can open websites. It can read content. It can go buy stuff. It's fake, of course. It's not actually buying anything. But it can go and do these fake transactions on this copy of Amazon, right? So it can do a bunch of different tasks. And it can also try to inform itself of what's going on. If it needs a calculator, it can pull up a tool that gives it access to a calculator, right? If it needs, for example, some knowledge or information it doesn't have, there's a copy of Wikipedia that it can go pull up and read. So now the model is not really just a single object that's sitting there. It's powering this agent that can go do a bunch of things. And it's free to take a bunch of actions to try to achieve some goal. Everybody see the difference between this and much more traditional kinds of LLMs? Cool. OK, so what kind of tasks should we use to try to evaluate whether the LLM can do a good job as an agent? Well, we can ask it questions that require some combination of these different things. Right, so for example, the first question would be, tell me how much I spent on a food purchase in March 2023. All right, so what would the agent have to do in that case? Well, it has to figure out that I have a bank account on the banking website, that it can go there, that it can find a place to click on list of transactions, that it can go in that list of transactions, go to the place for March 2023, pull up all the transactions that took place, and then filter out the ones that have to do with food, and then add all those together. Right? That's kind of the sequence of operations for what you would do to perform that task. And even though it's very trivial for us as humans, here you have to chain together a bunch of actions, right? The LLM has to take action 1, get the output, do something with that output for action 2, and so forth. And it has to know the sequence of actions, and it has to perform them all correctly. If it makes a mistake on step 2, then the final answer will be wrong for sure. So this is the kind of thing that Web Arena is trying to do. And when it came out, basically all the models were almost completely terrible at this. Even today, agents really struggle on a lot of these tasks. The more tools they have to use, the more complicated the reasoning of the set of steps they have to take, the more challenging these things are going to be. Just some other examples, and you can get pretty crazy of these. There's a lot of creative ones, right? Create a Nolan fans repo listing the director Nolan's Oscar-winning films in a README file. So you have to understand that there's a GitHub place that you can create a repo where you can instantiate the README file. And you have to go to fake IMDb, look up all the movies, and pull them into there, right? Again, some complex set of actions that you must take all in a certain order to get the task correct. OK, so this is Web Arena, very powerful. We have a bunch of other things of this type. For Web Arena, it was mostly focused on a handful of things. So shopping, which makes sense if you want to build an agent that's a co-pilot for you and helps you do this kind of thing. Shopping is a good application. Discussion forum, development, business content. These are the typical domains that you'll see for Web Arena. Cool. So other cases, and let me show you another example for Web Arena before I move on. Here's one with actual like fun maps, right? Create an efficient itinerary to look at all of Pittsburgh's art museums in a way that has minimal driving distance from some starting point, right? And log the order. This is actually pretty hard. Like, I couldn't do this. I would have to write a script myself to go do much of this. But in this case, it's going to have to first look up information about museums in Pittsburgh, like on Wikipedia. And then we'll have to go and get the map out, look at the starting point, run an algorithm, right, on the museums to figure out that itinerary, and then write it out to a different place. So quite non-trivial. All right. Let me talk another really popular one. So software engineering bench, SWE bench, is exactly this kind of thing, but it's explicitly for software development. So it's much more domain specific, but on the other hand, it's very, very useful. We really want to have agents that can act like software engineers for us. So we've gotten up to 70% on kind of the easier version of this. But here's the kind of thing that you do here, right? You're going to create some issue, for example, and show a list of code bases. And you give that to the language model. And you tell it, OK, go ahead and create a pull request that's going to fix this issue, right? And then we have a bunch of unit tests for all of these tasks. And we'll go ahead and evaluate the model on these unit tests. So this is actually not as distant as kind of Web Arena. We saw examples of this when we were doing RLVR. But it can get pretty crazy as well. The tasks can be very, very complex. You might have to pull in a lot of information and have a pretty complex path to be able to go out and do this. This as well was really hard initially for most models. Things have gotten better, but they're not extremely complex, so it's still quite hard. OK, let me show another example that's much more recent. This is called Terminal Bench. It's very similar in the sense that each task requires the agent to do tasks that are doable within the terminal. So these tasks can be quite diverse. You can see if you pull up the list, all the different things that can be done out there. So for example, you could have something like very old COBOL code, right? Modernize it. That's all typing into a terminal. Can my agent go out and do all the things that I need for that? There's cases where it's literally writing PyTorch, for example. And there's like 200 of these different tasks. You go ahead and run the agent in all of these and see how it can do. Current models are actually pretty decent at this. So Anthropic, which has the best code capabilities, or well, at least from my point of view, is currently leading the leaderboard. Notice two things, right? One is the choice of model. The second is the choice of agent. So all these agents are powered by models, but there are different agent harnesses that you can plug the same models into. And performance kind of depends on both, right? How good is my model in terms of its capabilities, but also what kind of harness do I build for it? So Terminal Bench is a nice one. Another example that I like is called Vending Bench. I encourage everyone to look at the website. So in this case, my LLM is going to operate this vending machine. That's the task. And when I say operate, I mean things like it can set the prices of the items in the vending machine. It can order new items if it realizes, hey, people are buying a lot of whatever. It can choose to get rid of some old items. Pretty much what you would do if you owned and operated a vending machine. But what's really being tracked here is over the long term, over a long period of time, can you make strategic choices that lead to making more money, or do you end up losing? And it's actually quite interesting to see how these things work out. You basically start out with some amount of money, and if you do a good job operating the vending machine, you can make more profit, or eventually you might go broke, right? So this is kind of what humans versus the top models are doing. Things are actually getting pretty good. Apparently, you can run a vending machine fairly well with a model. Now, Anthropic has actually a very nice blog post where they reveal all the details of what they did. At the time, which was a few months ago, their own agent did run out of money after a few months. And this is still a pretty big challenge. Like, keeping things coherent over very long spans of time is very, very non-trivial for models even today. OK, so I'm going to stop right there. But there's actually new agentic benchmarks coming out all the time, including some really interesting scenarios. So I encourage everybody to check out all the new ones and kind of what it takes to go ahead and build one of these things yourself. Cool. Everyone have a good weekend. Office hours this afternoon. Yep.
Yes. It is also getting created inside the model.
One thing you can do is to say, I don't care. right? I'll accept it, and I'll accept the fact that new models may, have had some access to this. The second way you can do it is by having a private. So when you go evaluate the models, you don't get to have it. You submit your model to someone that has that thing private. In which case, there's nothing you can do. But even then, there's ways of extracting information, right? So you have to have some level of you can't let them. But that's not the only other way. There's no magical way of ensuring things. Now, there's sort of good practices, right? Basically, there's a bunch of training. There that says build training. Similar to how, like, for training, there are certain lines of it in your using. Why is it going? And if people are nice, the answer is there's no good answer. Except for the private case.
Other ones, I think which is hilarious. There's one where it accuses the interaction agent of fraud.
Why does vending bench make them have external crises? Existential crises.
This isn't actually winning over the humans. This is like which model is winning ultimately, according to the judge. So this is just saying, hey, different cases of judges, which can be either models themselves or can be humans, they're all performing the same task. This task involves saying, oh, did I prefer this over that? What percentage of the time did they prefer the first way? So it's just saying, hey, how aligned are these curves? Right? What matters here is not so much like, are we higher or lower? What really matters is something along the lines of how close are we to the human, right? So if you see a curve that's close to the red curve, which is humans, that's good. You're correlated to the human very well. If you deviate a lot from the human, then probably you're mistaken. Exactly.
Actually, I recommend it to Zach if we have
They have some formula that normalizes by length. So if you have like extremely long answers, it says, hey, I'm going to cut off something. Or, hey, I'm going to decrease your score because you're constantly giving very long answers. I actually forgot the exact details, so you're welcome to check it, but that's all it's trying to do. If length is right, it's no problem, right? The question here is more like, if I don't need it, then you answer very long anyway. That's when you get penalized. So I don't think they actually force you to compress it. I think they literally score you down for unnecessary. Because they know the correct answers here. They have access to that. They just want to check to see that you aren't doing something crazy compared to the right answer. Sounds good. I have some point. That goal I can verify. So for example, the final goal in the examples that we showed were, well, did I get the amount of money in my set of transactions from March correct? Was it X correct answer? And I can check whether that answer is correct. Similarly, for the list of movies directed by Christopher Nolan, blah, 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 I can literally put information about the movies right there for you. So there's a single verifiable correct goal state, and you can check whether your agent reached that goal state or whether it didn't.
We're going to look for something heavy and hard.
For the video time posting or something.
For Web Arena, I don't think they do, but there are other benchmarks where you do get credit for intermediate. Yeah, it just depends on the way you want to design it, but you could give credit for them too.
All my kind of project and I'm trying to relate the distribution model. I'm wondering if there's anything.
Also gets me really quick.
We're talking about,
Classic.
How can I get more color on my backpack without biking through like different types of
Because I need to fine tune the model and more kind of semi real time, but the stable diffusion now still requires the prompt engineering because
Yep.
prompts short. But for example, you see that for the ChatGPT, it can put a lot of a very, very long prompt and
Right.
it can draw something like that. So I'm wondering if something that's more powerful than the stable diffusion and can digest the long prompt.
Right. I actually don't know. That's a good question. Let me do some reading. I would have suggested stable diffusion, but I'm not sure if there's something that's actually better than it. Yeah, let me see if there's anything newer that can handle long context text and is still runnable. And the hard part, if it's like way more powerful, it'll probably be bigger and harder to run in like one GPU.
Yeah, something like if I can access one A1
Yep.
or something like that still.
Yeah, let me check on that.
If I want to tune on my data set using the church and
Right.
store my fine-tuned weights on your server, or sometimes I need to do the embodied AI, like applying the
Yeah, of course.
the mammoth being code that I don't
If the
Right. Right. Yeah. Yeah, let's check on it. Yeah, feel free to do a literature survey and see if this is more powerful. I can do the same. But off the top of my head, I don't know anything.
So why don't you suggest the stable diffusion?
No, I mean, I would suggest stable diffusion, right? But if there's something more powerful out there, I just don't know what that is, so it's worth for us to look into it.
Okay, yeah. Thank you.
Yep.
Yeah, that's really hard. I think the question.
You can say that. I don't care.
because the
Sure. Why not? Yeah. I think it's okay. I'm not asking this because it's sort of restricted to ChatGPT. Gemini is fine too. I just didn't test it on Gemini, so I don't know what to expect. But feel free.
yes.
Yeah, in this question, basically, we want to give any example specific and not generalized over the internet, so that it can fail in the zero shot, but
Yes. Exactly.
Yeah,
Now,
because
I mean,
the logical questions they
yeah, I guess you want a question that's hard anyway, and then you can cross filter it. That combination will give you something challenging. Yeah, feel free to use Gemini. That's perfectly okay. In fact, I'm curious to see what Gemini does with these things.
and any model of Gemini Pro or
You probably want to use one of the worst models like Flash, because that will make your life easier. Right? Easier to make.
this evaluation metric. So there are was a specific metric and a general metric. So general metric is I think basically, but in specific metric, we have different metrics like whether it was something shining.
Well, you're supposed to make it up. I'm not suggesting there's a right answer here. Create something that you like.
So like how to like I'm not aware of like how to
Well, you want something for your particular distribution of characters, right? You want to measure what it looks like. So think through what that would look like. It's easy for you to empirically estimate, right, the output distribution of characters. What would you like it to have, right? You can say, hey, I expect it to be relatively close to uniform, or hey, I expect it to have same shape. You can measure those things, for example. But it's totally up to you, right? Feel free to do anything you like here.
So we have to measure the distribution and then like how
Well, usually that's supposed to be involved, right? That's what you have access to. You train your model. You can look at the token, which in this case is character frequencies. And that's pretty much the only thing you have to work with.
like is there
Well, intentionally, no, right? This is not you being creative. What do you expect this distribution to be?
Test I even said
You're going to take this output distribution, find a way of measuring it, and then think of what some properties that you would like to have. And if those properties are in the right direction, great. And if they're going in the wrong direction, then you're doing something wrong with your training. Well, think of just English language characters in general, right? What do you expect from them? There's some that show up very infrequently, there's some that show up very frequently, right? You kind of know which ones are which.
so in
Maybe
character
shows.
level like are they making sense or not? Are they a word or
Yeah, but here it's characters, so you're gonna have to go simpler than that, right? These are characters, so you cannot actually say anything about it. Do they make sense, right? All you can do is to look at how frequently they show up, and that's pretty much it. But you have plenty of information about that out there in the world, right? For example, you literally can look up English language frequencies, and you can say, hey, does mine match that? Is my distribution close to that distribution? Just an example.
Then I generated the output of Shakespeare.
I have to do that because like I'm not in the mood.
Now these are character levels, right? So it's very difficult to create highly complex speech. If you have a powerful GPU, you can get something.
So this implementation.
You do, right? Right. I mean, this will have to get trained, otherwise you're not going to.
It's optional, right?
Yes.
It's like
It is a bonus mission. You don't have to do it. Well, getting it done untrained, you won't get any good performance, right?
Like accuracy, we won't expect that accuracy will increase.
Yes, but you're not measuring accuracy at all in this case, right? At most, you're measuring perplexity. You have no access to the ability to answer questions correctly. But yeah, I mean, everything is just within the same nano GPT kind of structure to make it tractable for you guys to run stuff. That's the main thing here. Otherwise, you won't be able to, right? Because like you won't have the resources to train something more substantial. Just all character level, very tiny language models. That the best you can hope for is, well, they're matching the frequency of appearances of symbols. Maybe if you're lucky, they start looking like words, but that's the best you can really hope for here.
And we don't need can you use GPU like class GPU?
Yeah, you can.
Like
It'll be more powerful, yeah.
how to
Well, you'll have to get a place for it, unfortunately. Our class has no access to its own cloud resources. But yeah, I mean, like Google Colab, for example, is very easy to get set up. But you won't get too much more powerful. If you really want like a decent language model, you would need like 8 H100s training for at least a couple hours. And that's unfortunately out of reach. Yep.
Thank you.
So, can two teams present the same page? Is it like this one you don't know?
I'm gonna have to say no on that one, unfortunately. But if you guys have a debate about it,